All right, hi everyone, and welcome to another CBRG session. In today's session, we are going to go through how to perform differential abundance analysis using proteomics data. And the code that we'll be using is taken from Chapter 8 of Omics Data Analysis by Laurent Gatteau, and that's a book we've been following for most of this series. So to begin, as always, let's open up the project directory associated with this series, if you have such a directory. If not, that's okay, just open up RStudio. So as you can see, I'm already in the CBRG Meetups art project. So as always, go to your console and let's reinstall the CBRG package. So that's remotes : install GitHub Duke CCT/CBRG. And then you need to specify that force equals true so that it will override the package, or it'll replace the package if you already have it installed on your machine. Okay, so that worked fine. Once you reinstall the package, just go ahead and load the package. So that's library CBRG. And this will give you access to some of the functions that this package contains, including this one, launch_project. And this is meetup number 11. So we just put in 11 into launch_project. And if all of that works, you should see the project RMD file associated with today's meetup. So these are the, if you go to the setup chunk, you see that these are the packages that we'll be using in today's meetup. So once again, thank you to Paul for writing this nice code. So just go ahead and run all of it, as you can see, and then keep an eye on your console. If these packages are new to you, new to your machine, then it will likely take a little while for everything to install properly. If these packages are new to your machine, your console will also likely ask you for you to do something. And typically that means it's going to ask you if you want to install something else or you want to update something else. And in that case, definitely just say either yes, if that's one of the choices, or A, if that's one of the choices. All right, so now that I have all of these packages installed and loaded, I can go ahead and take a look at the data for today's session. So if you attended the previous session on proteomics, we encountered this dataset called CPTAC. And this is the dataset that is used by the book. And it's importantly what's known as a benchmark dataset. And briefly, the CPTAC study, which was now performed over a decade ago, it involved using these samples that contained a yeast protein or proteome background. And into this common background was spiked this sigma UPS1 standard that contained 48 different proteins. And different concentrations or different amounts of this standard was spiked into different tubes that contained this background yeast, these background yeast proteins. And the purpose of this was to create samples for which the concentrations of these 48 spike-in proteins were known, because those were controlled. And so since you know the answer, like you know that you're expecting, for example, in sample B to have 3 times the amount of these 48 proteins in sample A, whatever approach you use to quantify this differential abundance should give you the same answer. And all the other proteins, all the other background yeast proteins, there should be no significant difference across these, in this case, 5 conditions. The only statistically significant differences should be between these 48 proteins. So these 48 proteins serve as what are known as the true positives. And this benchmark dataset, although it was made in 2010, is still being used to develop different approaches to quantifying proteins. And that's what we will be doing today. We will be applying a few different approaches to try to see which one is quote unquote the best one in terms of picking up these true positive, these real differences in abundance. And so this is the whole this is meant to represent the whole CPTAC data set. We will only be using a fraction of this, a subset of this that only includes samples A and B. And you will see this number 6 appear a lot. That doesn't have any numeric significance in terms of the proteomics data. It's just that this was study number 6. So that maybe gets a little bit confusing, but that's what that 6 means. All right, so the first thing we want to do is load this CPTAC subset dataset into RStudio. And to do that, we can use this package called MS-Data. And once again, these data preparation steps are steps that I went through in the previous session, so I won't spend too much time talking about that today, but I will give a brief description of what each step is doing in case you haven't watched the previous session. So the first thing we want to do is on line 72 is if you run this line, so if you use this quant function from MS-Data and you set pattern equal to CPTAC, if you assign all of this to this object called f, if we go into the console and type in f, all f is it's an object that represents the location of where this CPTAC dataset is located on your machine. So that's all f is. And what we can do is we can use this information. We can supply it to this function called read.dlim, which then imports the relevant data. So it's this text file here. So if we go ahead and run line 76, we see that we get this pretty big data frame called prot_df. And if I just click on it, you can see that it importantly has this column called sequence. And these are the various peptide sequences that are in this data set. Additionally, it contains tons of other information, most of it which will not be relevant to today's session. But amongst all of this data, what is relevant are these, especially relevant, sorry, I keep moving back and forth, are these, we can't see them here. Let me just type it in. So if you want to see what all the columns are, you can just use the names function, do names prot_df, and you can see that these are the names of all the columns in our data set. And what we are specifically interested in, what we'll be using to do our differential abundance analysis, are data from these columns here, these here. Intensity 6A7, intensity 6A8, all the way up to intensity 6B9. And that is described in the book also. So to do that, we first collect the names of the columns we want to retain. And so we go to line 78. To do that, we take our prot_df data frame, the big one that we just took a look at. And then we use the select function from the dplyr package. And we use select we don't supply the names of the columns to the select function as we've usually done before. What we do instead is, rather than giving it the names of these 6 columns of interest, which, instead of typing out all 6, which is kind of error prone because you could make a spelling mistake, you can use what's known as a helper function. So in this case, it's contains. And so if we use this combination of, contains intensity and contains underscore, the only columns that have these 2 patterns are the columns of interest. And once we've selected those columns, we just extract the names of the columns. So if we run all of this, we get this object called call names. And as you can see, all it is simply the names of the columns of interest in this prot_df data frame. So now we have all the information we need to import these data into RStudio as a summarized experiment object. And the summarized experiment object is one that we've encountered quite a few times now in this series. And I keep going on about this because it genuinely is such a useful data type. The data frame is great. So this is a data frame. But This is great. Data frames are really useful if you are sticking to the, this one tabular data set. But the minute you start to do things like, so as you'll see, we'll be transforming our data, we'll be normalizing it, we'll be aggregating it. So basically, we'll be creating lots of new data using this original prot_df, data from this prot_df. So a summarized experiment object becomes a much more efficient way of keeping track of all of these new data sets. And importantly, these data sets remain connected to each other by virtue of being a member of the same summarized experiment object. So to create a summarized experiment object, we can use this function called read summarized experiment. And we need to supply it with a few things. One is the location of the data set of interest. So that's contained in this object called f. And then we need to specify which columns we want from that data set. So we can do this eCall equals call names, and call names is just simply the names of the columns of interest that we obtained on line 78. And then we can optionally specify this thing called fnames. Fname stands for feature names. And what this will do, as we'll see in a second, is it will, for the different, for the row names, it will apply the peptide sequence. So each row is associated with a particular peptide. And by setting fnames equal to sequence, the row names of the resulting data set will contain this peptide sequence information. And if that's a little bit unclear, I'll show you what that means in a second. And then since this is a tab separated file, we do sep equals \t. And we run all of this. We can assign it to an object called CPTAC. And I'm going to clear my console. I do this a lot. So in case you don't know how to do it, if you go to your console and use Control L, that just clears your console. So it's nice to do that from time to time. So if we take a look at our CPTAC SE object, we see that we get this information. It's a summarized experiment object. It has 6 columns and 11,000 and something rows. It doesn't have any metadata associated with it. And there are a few other pieces of information. As mentioned in previous sessions, these summarized experiment objects can be interrogated using a set of what is known as accessor functions that make dealing with this object easier. So one particularly useful one is this accessor function called assay. So if we do assay and give it the name of the summarized experiment object, what we can do is we can then pipe this into a function called view, view with a capital V. And if we do this, we see that we have a table that's opened up here next to our RMD file. And you can see that this assay contains the peptide intensities for each of our 6 samples. So we have 6 columns and we have thousands of rows. And we see previously when we set this fnames equal sequence, by doing that, each row here, its row name is associated with, its row name is the peptide that's associated with the row. So that's what assay does. There's another useful function called row data. And we do the same thing. We do row data D with a capital, data with a capital D, CPTAC underscore SE, and again, pipe this into another view object, another view function. We get this. Let me try. I think we need to subset this. Not like that. That didn't work. Sorry, give me 1 second. And 1 more second. Yeah, okay. So here's something new I learned. We can't pipe in this row data into the view function for some reason. So instead, we can just run it in the console. And actually, since there's quite a bit of information here, we can just put this within a head function. And we see here that what row data does is when we looked at assays, when we use the assay function, we got the peptide intensities for the different samples for the different peptides. Row data shows us that there is additional information associated with each of these peptides. For example, and all of this information is derived from that original prot_df data frame. And we'll see that these row data, again, we won't need most of it, but we will, when we come to it, we'll select the relevant row data, and I'll describe the row data columns that we'll be looking at. So that's row data, and finally, there's a thing called call data, and the function is called call capital D data. We do CPTAC_SE. You can see here that there is no information associated with the column data. And this becomes particularly important when we start doing our statistical analysis. And that'll become clearer when we do our statistical analysis. But given that this summarized experiment object doesn't contain any column data, we can create column data for it. And so to do that, you go to line 86. We'll do a couple of things. We will create a group column. And so this group column just contains information on the treatment sample. So what I mean by that is we go back here. So this CPTAC dataset contains, the subset dataset contains 6 samples. 3 of them correspond to this A treatment, and 3 of them correspond to this B treatment. So there should be 3 6As and 3 6Bs. So if we just do this, that creates this new group column. And another thing is, this is not relevant for the statistics later on, but just for the sake of completion, these 3, for example, 6A samples, 3 of them, there are 3 such 6A samples obtained from 3 different labs. And the labs are 7, 8, 9. And similarly, the 6B samples, those 3 samples were also obtained from 3 different labs, 7, 8, 9. So we create a group column, a sample column, and we look at column data again. We now see that there is this there's actually some information here. And as I mentioned, we won't be using the sample information here. I just included that because that's in the chapter. What we'll be looking at specifically is this group column. And so so the statistical analysis we'll be doing will be comparing this one group of A's. So these 3, you can think of them as biological replicates. We'll be comparing these 3 A's with these 3 B's. And that's it. So it's a simple comparison of 2 groups. I suppose if we had more data, this sample information, which tells you which lab the samples are coming from, we can use this as a blocking factor. But given that we just have 6 samples, we'll keep things simple today. All right, so we took a look at the row data for these peptides, and there's a lot of information associated with those peptides. What we're going to do is we're only going to keep 4 pieces of information. One is the sequence, the other is what's known as the leading razor protein. And so this is the identifier of the best scoring protein that a given peptide is associated with. We have this thing called a reverse column. So this, when the search is performed to try to identify which protein a given peptide matches to, 2 databases are used. One is called the target database, which, as the name suggests, contains bona fide targets of these peptides, and the other is known as a decoy database. And this is because a lot of what you see that is picked up, a lot of these peptide sequences that are picked up don't actually correspond to any actual protein. So this is one way of getting rid of what are called these reverse hits. So these aren't, you can consider this as noise. And there's another column called potential.contaminant, and this is again, I believe, interrogating a database of well-known contaminants. And so what we can do is we can take these 4 relevant column names and put it in a character vector and assign it to an object called keepvar. So if we just run keepvar in the console, we see that it just contains these 4 relevant names. And so what we can do is, if we go to line 94, is we can use this keepvar, which contains these 4 names. We can use it to subset the row data, meaning we can use this to only select these 4 columns from our row data, which contained many more than just 4 columns. And so to do that, we do row data CPTAC underscore SE, and then we use this common brackets notation in R. We do a space, and I'll make this obvious by putting it here, comma. And so what this means is we want to keep all the rows. So all the rows meaning all the peptides. And then keep var after the comma. So we only want to keep these 4 columns. And then we assign all of this back, not to CPTAC underscore SE, but to row data CPTAC underscore SE. If we run all of that, we get, and if we run row data again, underscore SE, and we pipe this into head, we see now, instead of having many columns associated with these different peptides, we just have 4 columns, right? Okay, so quickly moving on to the next step, the CPTAC data as it is here contains a lot of 0 values, and these are supposed to represent NAs. And so the way to deal with that is there's this handy function called 0 is NA. So it does what it says. It just goes through your data set looking for all the zeros and converts them to NAs. So we explicitly define those as missing values. Now, dealing with missing values is anyway a complicated issue. Just discarding the information is generally not a good idea because you discard information. So that leads to this thing called imputation, where you come up with some kind of strategy for replacing these data. And this becomes even more complicated with proteomics data because you have some kind of data that are missing at random and some that are missing not at random. And you have to use different strategies depending on the type of missingness. So to not deal with that today, and the chapter 8 of the omics data analysis book also decides to kind of gloss over this rather difficult section. What it does instead is it only keeps those peptides that have, or rather it removes those peptides that have 4 or more NAs. And to do that, you can use this filter NA function. We apply it to the summarized experiment object, and you set this parameter PNA equal to the fraction that corresponds to your threshold. So if we do that, and then we overwrite the CPTAC underscore SE object like this, we do that on line 100. And so that's kind of all the pre-processing we do with the summarized experiment object. What we then need to do is we need to convert it to a Q features object, which is very similar to a summarized experiment object, but it contains, or rather it is, you can use proteomics specific functions with this object type. And so to convert a summarized experiment object to a Q features object, you can just do a list, give it a name. So this, if you say peptides equals, then the assay that the subsequent Q features object will contain will be called peptides. And then we can assign it to an object simply called CPTAC. Now, unfortunately, if we do, for example, call data CPTAC, we see that converting to this Q features object gets rid of the column data, and we need to keep that. So to do that, we can just simply extract the column data from the summarized experiment object and assign it to this new Q features object. And so now we see that we have imported our column data. And just to show you that this is kind of the same thing. If we do assay, we can again apply this assay accessor function to a QFeatures object. If we just do assay CPTAC, pipe that into view, we see that we've not really done anything. This is just like the information that we had in our summarized experiment object. So all we've done is kind of changed a summarized experiment object to a QFeatures object. Now comes the important part of, why did we retain that reverse and potential contaminant information for our row data? And that's because each of those columns contains information on whether or not the corresponding peptide is either a reverse hit, meaning we want to get rid of it, or if it's a potential contaminant, meaning we want to get rid of it also. So these reverse and potential dot contaminant columns, they either contain nothing, meaning, keep that peptide, or they contain a plus. And so all peptides that have a plus associated with either of these, we need to remove them. So to do that, we can use this filter features function. So we do CPTAC, pipe it into filter features, and the notation is to use this formula, our formula notation. So we do tilde, and then reverse does not equal plus. So meaning we want to filter in, or we want to keep those that don't have a plus. And similarly, we do the same thing for potential contaminant. And so by running this step, line 107, we get rid of all our reverse hits and potential contaminants. We're now ready to transform our data. And so we're going to do two transformations. One is a log transformation, because if you plot the original raw peptide data, you'll see that the distribution is highly non-normal. And since the statistics we'll be doing downstream assume this normal distribution, one way to arrive at something that approximates a normal distribution is to do a log transformation. And we use this log transform function here. We supply it with our CPTAC QFeatures object. And then we give it the name of the assay that we are log transforming. And this CPTAC object currently only contains one assay. And actually, to see that, you can just type in CPTAC into your console, and you see it just has one peptides, right? Just one assay. So we take that assay, we log transform it, and since we're log transforming it, we're creating new data. We're basically creating a new assay. And so we need to give that assay a name. And so we can call that log peptides, which makes sense. So if we run all of this and type in CPTAC again into the console, we now see that the CPTAC object now contains two assays, our original peptide data and our log transformed peptide data. After we've log transformed, another useful thing to do is a thing called quantile normalization. And for example, these we would expect the distribution of these log transformed peptide values to be very similar between different runs and certainly across labs. And that's because most of the proteome is assumed not to be changing, which is true in this case, because most of the proteome is just this identical yeast proteome. There are only 48 proteins that are supposed to be differentially abundant. However, due to technical reasons, these distributions sometimes don't align the way they're supposed to. So one way to get around that is to do some kind of normalization. So this could be median normalization, or in this case, we're choosing to do quantile normalization. And you can see that this normalize function works very similar to the log transform. We use the CPTAC object. We give it the name of the assay we want to normalize. So in this case, we're doing log peptides and not just peptides. We give it a name. So this is the resulting assay. So that's called log norm underscore peptides. And we specify a method of normalization. So I said quantile normalization, so we do method equals quantiles. If we run that, and again, remembering to assign it back to CPTAC, if we run CPTAC in the console, we now see we've created a third assay. So I hope that this at least demonstrates how we can use this QFeatures object to sequentially create new assays based on these various transformations. So in this way, we have a record of what we're doing, and we keep all of these different assays in the same place. And so we can see the kind of logical flow. We started off with raw peptide intensities, we log transformed them, and then we normalize the log transformations. Okay, so that's kind of all we have to do for the pre-processing. Now we are ready to aggregate our peptide intensity data so that we have protein level data. So, and this is because you frequently have multiple peptides that correspond to the same protein. So each protein is then associated with multiple intensities. And what you want to do is you want to arrive at one aggregate number that represents all of those different peptides for each protein. And you can use that in protein level intensity information to do your statistics. So we look at a few ways of aggregating these peptides. So to do this aggregation, we will, these different types of aggregation, we will always use this aggregate features function. And the way this works is quite similar to the log transform and normalize functions that we just used. Again, we supply it with the CPTAC object. We give it the name of the assay we want to aggregate. So these are the log norm peptides. We give it the name of the resulting assay, once you've performed the aggregation. And then we need to specify a feature column that we're doing this aggregation on. So what I mean by that is, so this leading razor protein, this contains the names of proteins. And so by giving it this information, you are telling QFeatures that you want to summarize the peptide level information, so the peptide intensities, you want to summarize them by protein. So for example, if there are 6 peptides associated with something called protein A, what this will do is it'll take those 6 peptides, aggregate them, and give you one value for that corresponding protein. And the aggregation function we are using in this case is the medians. The median. So this will take so if there are 6 peptides associated with the protein IGF-1, what this will do is it'll work out the median of the 6 intensities for the 6 peptides and give you one value that represents the intensity of the IGF-1 protein. And then finally, we specify this na.rm equals true because our log norm peptide data still contains missing values, and we need to ignore that when we're working out our medians, otherwise we'll encounter an error. So if we do all of that, remembering again to assign to CPTAC, and if we run CPTAC in the console, we now see we have a 4th assay. And one thing to notice with this assay compared to the previous 3 is the number of rows, right? We started off with 7,546, each one corresponding to a different peptide, or to a peptide. And this, if we look at the proteins median, proteins_med assay, we now see we have far fewer rows. And that's because we've performed this aggregation. So we've gone from these 7,546 peptides to 1,398 proteins. So that's the way of getting the median aggregation. So we can do similarly, we can just sum up the peptide information. So it's the same, basically the same code, except for 2 differences. One, we obviously have to give the resulting assay a new name. So proteins_sum seems reasonable. And we have to specify the different function. So instead of call medians, we use call sums. And again, we assign all of that back to CPTAC. And if we run CPTAC in the console, we now see we have a 5th assay. So again, I hope you can see, like, by doing all of these things, we are generating lots of new data. And so it's becoming even more difficult to keep track of these different assays and how they are connected to each other. Once again, this QFeatures object allows us to do that in the not a pain-free way, but the most painless way, pain-free way. So we did median aggregation, we did sum aggregation. Let's now do mean aggregation by mean. So I'm just going to, I'm not going to go through this code here because this is just like median aggregation. And the last 2 types of aggregation we'll do this thing called median polish and robust summary. and especially given the time, it would be very difficult to cover both of those in detail. But briefly, what they are both trying to do is take into account what's known as the peptide effect. So one thing that is one of many things that can result in complications with proteomics data is the fact that different peptides that correspond to the same protein can, for physiochemical reasons, have different intensity values, even though they are equally abundant. And so this is known as a peptide effect, and it's an artifact that has to be taken into account. And so there are different approaches to doing it. So one is this median polish method, which, as I understand it, is you are kind of subtracting this peptide effect. And to learn more about median polish in general, there's a nice reference here that I've included. And robust summary is, it explicitly models this peptide effect when it's working out this summary intensity value for each protein. And again, to learn more about that, refer to section 2.7 of this paper. It's not especially well explained, as in to a lay audience. So if you really want to learn more about this, I think the best thing is to consult your local biostatistician. But the good thing is, at least in terms of running the code, it's super easy. You just do this msco utils : median polish, or msco utils : robust summary. And so if we run both of those, you can see this takes a little bit longer to work out than it does to work out median and mean. If we finally run CPTAC in the console, we now see that we have 8 different assay types. That's because we've done a lot of transformation to our data. And so now what we'll do is we'll do statistical analysis, this differential abundance analysis, using these 5 different sets of protein intensities. So to do our statistical analysis, we will be using this familiar package called Lemma, which we've previously encountered when we were doing microarray analysis. So I'll walk through the steps. The good thing is, once you write the code for one round of Lemma analysis, the subsequent code for the other different data sets is almost identical. So you can just do a lot of copy pasting. So let's take a look at the Lemma package, the Lemma approach. The first thing we want to do is we want to extract the assay of interest that we'll be using for Lemma. So we'll go through these. So we aggregated our data in 5 different ways. We'll go through these 5 aggregations step by step and compare the resulting, we'll compare the results. So we'll start off with the median aggregation. So to do that, to extract it, we can do CPTAC, square brackets, and then the name of the assay, proteins _ median, and we can assign it to an object called prots _ med. Now, the thing about doing this kind of subsetting is we lose the column data for some reason. And we need that column data to perform our statistics. So we have to reassign the column data from CPTAC to this prots med object. So we do that on line 168, right? And just to remind you of what this col data is, we just do col data prots _ med, and we see that specifically it contains this group information, which is what we'll need to do for our statistical analysis. So we go to line 169. The first thing we do, again, this hopefully should be a little bit familiar from the microarray, and actually even the RNA-seq walkthroughs. To do this statistical analysis, we first need to create what's known as a design matrix. And to do that, we can use this model.matrix function. We do tilde, and we give it this group information, right? By doing prots _ med $group. So let's go ahead and do that and take a look. We'll take a look at the design _ med to see what the purpose of this line was. And so this is what a design matrix looks like. So this is a really simple one. And so, again, to remind you from a few sessions ago, what we're doing is we're fitting a linear model for each of our proteins. And what this is doing is it's trying to determine for each protein, is there a statistically significant difference between the mean A values and the mean B values? And this, I won't go into the details of this because this has been covered previously. This is one way of telling Lemma that this is the comparison you want to make. So we specified the design matrix, and then the next step is to do a two-step fitting procedure. One is to use this lmfit function, and we give it our protsmed information. So you have to do assay protsmed, because to show you, if you just did protsmed, you get this information. That's not what you want. What you want is the information within protsmed. So we can do that using this assay. So you can see we have various proteins and various intensities associated with the different groups, the different samples. So we do the first fit step, line 170, and then we do this thing called empirical Bayes. And this is another thing that was covered previously, and this is why we do Lemma. Lemma takes advantage of the fact that we're making various measurements, and it rather than using the variance associated with a particular measurement to work out the statistics, what Lemma does is it works out a weighted average of an overall variance that it calculates using all of your data and the measured variance. And this is something we've looked at for microarray analysis and RNA-seq. This empirical Bayes approach cuts across various omics types, analysis types, and is a way of making your analyses more powerful. Right, so we just do eBayes on this fitmed, so that's our second step. And that's it, we've performed this is all, so whenever you hear people say Lemma, they're basically talking about these 3 lines and one more line after. So it's essentially just a 4-line process. Okay, so we have this fit_med, and if we take a look at it, it's not particularly obvious what it's actually done. So we have to do a little bit more work to extract relevant information from this fitmed object. And by relevant, I mean especially 2 things. One, the calculated log fold changes between group A and group B, and the associated p-values. And so to do that, we can use this other function from Lemma called toptable. And toptable takes in this fitted object, fit_med. And if we go back to the design matrix, design_med, we see that this simple linear model has 2 coefficients. It has this intercept term and this beta1 term. And this is the term of interest. This is the one that represents the difference between the mean group A protein intensities and the mean group B protein intensities. So this is the one we want to use to do our stats on. And so the name of that coefficient, as you can tell here, is protsmed $group 6b. So that's the name we supply here. And this number equals infinity we set to tell Lemma that we want comparisons for all the proteins. Otherwise, it'll give us, I think, only the top 250 or something like that. So actually, just to see what this does, we can copy this into the console, right? And then just type in view. And you see that this is the result. We have a log fold change, t statistic, p-value, adjusted p-value, and we have the different proteins. And this is great. This is exactly what we want. And importantly, notice that the most significant changes to the lowest p-values are associated with these human proteins, which is a relief. Like, that's what we want. We want the yeast proteins to be all, approximately the same between the 2 groups. It's the human proteins that we want to see. We want our method to pick up on the fact that the human proteins are the ones that show this differential abundance. So that's really what toptable does. Actually, let's take a look at that again. One thing you'll notice is the names of the proteins are all row names. Or rather, all the proteins are row names. And so what we want to do is, dplyr in particular doesn't like data frames with row names. It just doesn't like row names in general. So there's a function called row names to column. So whenever you have a data frame that has row names and you want to explicitly make those row names, assign those row names to a new column, you can use this row names to column function and give it the name of the new column. So if we want to see what all of this is doing, again, you can just copy this into the console and type in view. And so now we see this is exactly like the previous data frame, except that this data frame doesn't have row names. It just has the protein names as their own independent column. And this is just much nicer to do when you're using dplyr. And then we convert it to a tibble, which is a special type of data frame associated with dplyr. And then we do this one additional step where what we want to do is we want to create a column that tells us whether a given protein is a true positive or a false positive. So true positive meaning, is it a human protein? And not true positive meaning that it's a yeast protein. So to do that, we can create a new column called TP. And this will make sense in a second when we do our visualization, right? This is a way of highlighting the human proteins in our visualization. So we do TP equals, and we can use this function called string strdetect from the package called stringer. And all strdetect does is, for a given column, so this proteins column, it's looking for a particular string pattern. And so the particular pattern it's looking for is this UPS. And the reason we put in UPS is the only proteins that have this UPS in their names are the human proteins. And string detect produces a Boolean. So meaning it produces a true or a false. So if we run all of this and assign it to an object called res_med, let's take a look at that. We see that we've created this new column that has a true if it's a human protein and a false if it's a yeast protein. That's it. And we can use this res_med function to make a volcano plot. And since this is something we've done previously, I'm going to skip the details, which should now be familiar, of how to make a simple volcano plot. So if we run all of this, we get our final visualization of our results. And so you can see here that this dashed horizontal line represents kind of this is the adjusted p-value that is equal to 0.05. So we can use that. If we use that as our threshold, we see that the only red dot, meaning the only true positive that is above that threshold, there's only one. So just doing this median aggregation followed by lemma misses out all the other true positives. So it only gives us one if we use this this adjusted p-value threshold. And that's not great because we would expect a lot more to be in this quadrant up here. So what we can do is we can just repeat this lemma process for all the other aggregations. So let's go through this. So I'm just going to run through this without explaining because this, if you compare it to the previous code, is basically identical except you change the names from med to sum just to keep track of the different things. We do this. And so now if we look at the plot for the sum aggregation, one thing I do have to confess is I only realized somewhat belatedly that look at the log fold changes, they're incredibly high. So something, when it comes to sum aggregation, I need to talk to, I guess I'll talk to Paul about this. The order in which you do the pre-processing of the data clearly matters here. So something went wrong with the sum aggregation. So given that the log fold changes are so absurdly high and not in line with reality, I'm not going to take this, the fact that many of the true positives appeared in this quadrant, I'm going to take this with a grain of salt. So I apologize for this. I'm going to skip the sum aggregation for now. Moving on to the mean aggregation, again, just running through the code super quickly, we get this plot. And if you compare it to the median aggregation, where we only really picked up on one true positive, right, in this quadrant, if we do mean aggregation, we now pick up on two true positives. Again, not great, but it's slightly better than median. Now, if we compare this these sort of more naive approaches to the more robust approaches, so median polish and robust summary, we should hopefully see an improvement. So again, I run through all of the lemma for median polish and plot these data, and you now see this is a dramatic improvement on mean and median normalization. So aggregation using mean and median is clearly problematic. So if we use this median polish method, we see that we're picking up, again, it's not perfect. One thing to emphasize at this point is another reason, potential reason that this is not perfect is I didn't do any data imputation, right? So I'm sure if I did more sophisticated and appropriate pre-processing, it would improve the results. But in this case, since we're kind of comparing, like we're using the same input for these different aggregation methods, I think it's still fair to it's still a fair way of comparing these different aggregation methods. So anyway, we see that we're not picking up on all the true positives, but we've vastly improved our performance. And so that's with median polish. And if we do robust summary, we see that this ends up performing the best. Of the, I forget how many, if we go back to the book, and so again, this just reproduces exactly what's in the book. We scroll all the way down. So this plot here is just a slightly nicer looking version of this plot here. But see, just like they picked up 21 true positives, so did we. But we are still missing 12. Right. So that's that. We have 9 minutes left, but I'm not actually keeping an eye on YouTube, so I don't know if there are any questions. But if there are any questions, I'll take a look at them after this session, or please email any of us about this. So this was, again, quite a lot of stuff, especially the theory behind median polish and robust summary is admittedly quite heavy. So please, if you're interested, go through these references, and again, reach out to any of us if you have further questions. But hopefully, I hope that at the very least you leave this session with an appreciation for the effect that this simple aggregation of peptide level information into protein level information, the dramatic effect these different aggregation methods can have on your resulting statistics. And not taking into account these peptide effects can lead to issues. So with that, thank you for your attention, and yeah, hope you have a good day.